In this section, we're going to be going over how to calculate limits using limit laws. So previously, we were calculating limits either using a table or looking at a graph. Now we're just going to calculate them by hand using these limit laws that we're going to learn. Okay, so starting with the limit of a constant function, this is going to be the easiest one. We know a constant function is just a function f of x equals c, where c is just a number, so like f of x equals 2. And we know graphically speaking, they're just horizontal lines at that c value, right? So if we're trying to calculate the limit of f of x as x approaches a, where f of x is equal to c, so we're trying to find the limit of c as x approaches a, the answer is always going to be whatever that constant function is. Okay, so the reason for that is no matter where you are on that whole entire horizontal line, no matter where you are, the function is always going to be at that c value. Okay, so now let's use actual numbers, so hopefully it makes a little more sense. Let's find the following limits. The limit of 7 as x approaches 4. So based on what we just learned, the answer is just 7. And the reasoning is, if we have a graph of this, and we have a horizontal line at 7 on the y-axis, that's y equals 7, or f of x equals 7, and then you go over to 4, the function is obviously going to be approaching a function value of 7 because it is always equal to 7. So this could have said as x approaches -1,000,000, and the answer would still be 7. Okay, next one, the limit of -5 as x approaches 0. So this answer is just -5. You can draw a graph for that one as well if you want. Okay, so those ones are the easiest one for a constant function. Next, we have the identity function. The identity function is the function f of x equals x, or y equals x. It's called the identity function because x and y are always equal to each other. It's the identity. And graphically speaking, it is a line with a slope of 1 that goes through the origin. Okay, so if you're trying to find the limit of x as x approaches a, it's always going to equal whatever the a value is this time. Okay, so graphically speaking, this is what it looked like over here on the right, and as x approaches a, it's going to equal a because it's the identity. As x is approaching a, the y value will also be a based on the definition of the function. Okay, so let's go ahead and see an example. Let's find the limit of x as x approaches -7. Based on what we just learned, the answer is -7. Okay, and then graphically, let's take a look. If we had y equals x, and we had -7 for x, and this is what it's approaching as x approaches -7, then that x value, or that y value rather, will also be -7 because y equals x. Okay, and then the next one for b, we have the limit of x as x approaches pi. That's just going to be pi. Okay, pi is just a number, so we just leave it just as pi. So hopefully those ones were pretty easy, and hopefully they make sense graphically. If you can think about things doing it by hand and then think about the graph, what's going on with the graph, that's going to help you out a lot. Next thing, we're going to get to the limit of a sum. So the limit of a sum is going to be if we have one limit, the limit of f of x as x approaches a, if that equals L, and then we know another limit of g of x as x approaches that same a equals m, then if we're trying to find the limit of the sum f plus g, then what we can do is split it up. We could do the limit of f plus the limit of g. Since we know both of them, then we can just add the results, L plus m, which were both what they were both individually. Okay, so hopefully this kind of makes sense. Also, it's kind of painfully obvious. It's almost like you're distributing the limit to each of these. Technically, it's not distributing, but it's kind of like you're distributing the limit. Okay, so let's see an example. We want to find the limit of x plus 9 as x approaches -4. Based on what we just said, that's going to equal the limit as x approaches -4 of x plus the limit as x approaches -4 of 9. So we do them separately. The first one is the identity one, that's -4. The second one is a constant one, which is 9. So -4 plus 9 gives us an answer of 5. Okay, so for that function, f of x equals x plus 9. As x approaches -4, the function is approaching 5. And we're going to see a simplified version of some of these rules in certain cases in a little bit. Okay, the limit of a difference. This is the same exact thing as what we just did, except for it's not addition, it is subtraction. So let's just skip right to the example. The limit as x approaches 5 of 12 minus x. So based on the example, based on what we just did, that's the limit of 12 minus the limit of x as x approaches 5. So the first one is constant, so that's a 12. Second one is identity, so that is a 5. 12 minus 5, we get 7. Once again, hopefully a piece of cake so far. Okay, next one gets a little bit harder. The limit of a product. So it's the same idea. If the limit of f equals L, the limit of g equals m. And if we're taking the limit of f times g, we can split it up and do the limit of f times the limit of g. And then just multiply their results separately. And I will make one little note, is you can only do this when they both exist separately. We'll see some cases where you're tempted to do this, but then one of them doesn't exist, so you can't actually split it up like this. So let's do an example. Let's find the following limits, and this is going to seem a little silly the way that we're doing it now once we know the shortcut, which you probably already catching on. So the limit of -6x as x approaches 5. So we do them separately. We do the limit of -6 times, that should be times the limit of x, and now we just have to do them separately. The first one is a constant, the second one is a identity. So -6 times 5, we get -30. Okay, next one we have the limit of 7x minus 4 as x approaches -3. Let's go ahead and split this up as the limit of 7. I'll start first like this. The limit of 7x minus the limit of 4. So I'm just using that difference property. And now we can actually split the first one up using the product property. So that would be the limit of 7 times the limit of x minus the limit of 4. So all I'm doing is splitting up as far as I can go, make it a little bit easier on us. And now it's going to be, this first one is a constant, so 7. The next one is a identity, so -3. And the last one is a constant, so 4. 7 times -3, -21 minus 4, we get -25. Okay. And last one for this example, we have a limit of -3x squared as x approaches 2. We're going to start by splitting it up like this. The limit of -3 times the limit of x squared using that product rule where we can split it up using multiplication. And that's going to be the limit of -3. We could actually split up the limit of x squared as the limit of x times the limit of x, right? Because x squared is x times x. Now we can do these all separately. That's going to give us -3 times 2 times 2, which is -12. Okay, so moving on to the next property is the limit of a power. So if we have the limit of f of x equals L and n is some positive integer, if we are doing the limit of some function raised to an exponent, what we can do is first we can do the limit of the function, get an answer, and then raise the answer to the exponent afterwards. Okay, so let's go ahead and see how this is done. We want to find the limit of 2x minus 7 cubed as x approaches 5. So using the rule we just did, we're going to first calculate the limit of the base, which is 2x minus 7. And then after we find an answer, then we're going to cube the answer. So we're going to go ahead and find that limit. I'm going to actually skip to the answer for 2x minus 7 just because we did a bunch of them. That's going to end up being 3. And then 3 cubed, we get 27. Okay, and then I just put a little note on the side that that equaled 3. Next one, we have the limit of 3x minus 5 cubed as x approaches 4. So once again, we can rewrite this as the limit as x approaches 4 of 3x minus 5. We're going to find that first, get an answer, and then we're going to cube the answer. So if we went ahead and did that, we would end up getting 7 for the limit of 3x minus 5. And 7 cubed, I think, is 343. Let me check. Yes, 343. Okay, so next, limit of a root. This is essentially very similar to what we just did. Instead of a positive exponent, we have some sort of root, square root, cube root, fourth root, and so on. If you're taking the limit of a function under a root, you can take the limit of the function first and then take the root of that answer. Okay, let's see these examples. We have the limit of the square root of 4x squared plus 5 as x approaches negative 2. So based on this rule, what we can do is take the limit as x approaches negative 2 of 4x squared plus 5, find an answer, and then take the square root of it. Okay, and then when we're doing that limit inside, we should get 21. So the answer is the square root of 21. I'm going to leave it just like that because it is an irrational number. Okay, and the next one, we have the limit of the square root of 6x squared minus 4 as x approaches 1. So I'm just going to pause it and fill everything in. Maybe you can pause it right now and try it yourself. And for this one, you should end up getting the square root of 2. Okay, so let's move on to the next one. And this is actually the last property, and then we'll move on to something else. So the limit of a quotient, exactly what it sounds like. Same thing as like the product one, except now we're dividing. So if you're doing the limit of f divided by g, you can do the limit of f and divide that by the limit of g separately. So do them separately, numerator and denominator, and then divide your answers. So for example, let's find the limit of the quotient x cubed minus 3x squared plus 7 divided by 2x minus 5 as x approaches 1. So based on this rule, based on this law here, we're going to do the limit of the numerator, and then we're going to do the limit of the denominator separately, and we're going to divide the results, and then that will be our answer. So I'm not going to show every single step here because we already did this in the past few minutes here. So the limit of the numerator, we should end up, technically we would do the limit of x times the limit of x times the limit of x minus the limit of 3 times the limit of x times the limit of x plus the limit of 7. Technically you would do that, and you would get 5 in the numerator. In the denominator, calculating this limit just like we have been in the past, we would end up getting negative 3. So our answer will be negative 5/3. Okay, and then for this next one, we have the limit of x squared minus 4x plus 1 over 3x minus 5 as x approaches 2. So once again, let's set up doing the limit in the numerator divided by the limit of the denominator, and we're going to do them separately and then divide the answers, and then we will be done. So if we calculated the limit in the numerator, we should get -3. In the denominator, we should get 1. So -3 over 1, this gives us an answer of -3. And when you're doing these limits, just always remember what you're actually doing. You're saying, in this case, as the x value approaches 2, the function value for this function will be approaching -3. So as x gets closer and closer to 2, the y values get closer and closer to -3. So here's a summary of these properties. You can just kind of take a glance at them if you want. I just have them here so they're all in one place. They're everything that we just mentioned though. Okay, so hopefully when you were doing these problems, you were just thinking to yourself, well, these rules are kind of obvious. All we're doing for the most part is just plugging in the number and evaluating it. So that's true, and that has to do with the fact that these functions were continuous where we were plugging them in. So this brings us to the direct substitution property, and we're going to be talking about polynomials and rational functions here. So if the function is a polynomial or rational function, we know polynomials are smooth and continuous functions everywhere. And we know that rational functions are continuous everywhere over their domain. So they're continuous essentially where there's no holes or no vertical asymptotes. Okay, so direct substitution property says if we're doing the limit of f of x as x approaches a, all we have to do is evaluate f of a. So that means all we have to do here is take the a value and plug it into this function, and that is our answer. So it's a lot shorter than what we've been doing, and we get the same exact answer. And this is based on continuity, and we call it the direct substitution property. So let's find the following limits. We want to find the limit of 4x cubed plus 2x squared minus 6x plus 5 as x approaches 3. So before we said that we would have to break this apart using the limit rules, and it seems like a huge waste of time. All we have to do is recognize that this is a polynomial. This is a polynomial. It's continuous everywhere. We can use the direct substitution property. We can plug in the 3 into all of the x's and just evaluate. So 4 times 3 cubed plus 2 times 3 squared minus 6 times 3 plus 5. Make sure your order of operations are good, and you should get 113 here. Okay, so same idea for the next one, the limit of 7x cubed plus 3x squared minus 4x plus 3 as x approaches 0. This function is another polynomial. It's continuous everywhere, which means we can plug in the 0. And hopefully we could do this one in our head. 7 times 0 cubed plus 3 times 0 squared minus 4 times 0 plus 3. This answer is just going to be 3. Okay, and then the last one here is a rational function. But since what we're going to be plugging in, the -1, is in the domain, meaning it's not going to make this denominator equal 0, then we can go ahead and use the direct substitution property and plug it right in. So that's going to give us -1 squared minus 3 over -1 plus 5, which will be -2 over 4, so -1/2. So it simplifies to -1/2. Okay, so basically, if you can use direct substitution, just like what we just did, then do that, and it is a piece of cake. So, but however, you won't be able to always use direct substitution, as we're going to see right now. So we have these other techniques used to evaluate limits, and the two commonly used techniques that we're going to be using are going to be factoring and rationalizing the denominator or numerator. So I'll just say factoring and rationalizing. The way we're going to rationalize the denominator or numerator is multiplying by the conjugate. So we'll mention that once we get there. Okay, so first example, let's find the limit of x squared minus x minus 6 over x minus 3 as x approaches 3. So immediately you should say, okay, this is a rational function. So you might think that direct substitution would work, but if you tried to use direct substitution, you would end up simplifying it to 0 over 0. 0 over 0 is not a number. 0 over 0 is indeterminate form, it's called, and that does not work. That doesn't tell us anything, which it means that we cannot do that. So first, we're actually going to have to try to factor this. So typically, if that happens with rational functions, that's kind of your hint that you should try to factor it. We can factor the numerator as x minus 3 times x plus 2. And now we can recognize that the x minus 3's cancel. And what we are left with is the limit of x plus 2. Technically x plus 2 over 1, but then we obviously don't have to write that. And now we can use direct substitution, plug in the 3, and we get 5. Okay, so always remember that 0 over 0 is not an answer. That's indeterminate form, not an answer. Okay, let's go ahead and check this one out. The limit of x squared plus 2x minus 3 over x squared minus 1 as x approaches 1. So once again, direct substitution will not work. We would end up getting indeterminate form again. So I just wrote it down, indeterminate form, just so we have it in our notes for now. Okay, so let's go ahead and factor. So we can factor the numerator. The numerator factors to x plus 3 times x minus 1. And the denominator factors to x plus 1 times x minus 1. We can cancel off a common factor of x minus 1. And we are left with x plus 3 over x plus 1. Now we can go ahead and use direct substitution, right? So we plug in our 1. So that's 1 plus 3 over 1 plus 1. That gives us 4 over 2, which is 2. Okay, so that is solving these using the factoring method. Now let's see one where we have to rationalize the numerator. So we want the limit of the square root of 4 plus x minus 2 over x as x approaches 0. So before we do that, let's recall something with these conjugates. Let's recall that if we multiply conjugates, a plus b times a minus b, we get a squared minus b squared. So if you didn't remember that, hopefully you do now. If you multiplied that out, if you FOILed it out, then it would end up canceling to a squared minus b squared. So these are conjugates. They're the same two terms, one separated by addition, one separated by subtraction, and they're called conjugates. So a plus b is the conjugate to a minus b. Okay, so we're going to be using that right now. The hint to do this, so let's first recognize that we can't do direct substitution. Okay, so we should always do that first, just recognize that you can't use direct substitution. So let's take a look at how would we know to rationalize the numerator. So the hint that we know to rationalize the numerator is this square root term and then plus or minus a number. So there's two terms in the numerator where one of them is a square root. Okay, so that's a huge hint that you need to do this. Obviously it says here to rationalize the numerator, but it won't always say that for you, so you need to recognize it. So we're going to multiply by the conjugate of the square root of 4 plus x minus 2. The conjugate of that is going to be the square root of 4 plus x plus 2. So if we multiply it in the numerator, we also have to multiply it in the denominator, so we're not changing anything. And now we're going to get the limit as x approaches 0 of, so here's the thing, here's the shortcut that we just wrote down up here. You do not want to have to actually FOIL this out. You can, it's not the end of the world, but the shortcut is that it's going to end up being the first one squared minus the second term squared. So the first term here is the square root of 4 plus x. Taking the square root, squaring the square root will make that just 4 plus x. It's going to cancel, right? So the first one squared is 4 plus x. The second one squared is 2 squared, which is 4. So all I did was use the shortcut. I said it was the first term squared minus the second term squared. If you forgot that, you would have to FOIL it out, and you should get the same thing. Okay, in the denominator, what I'm going to do is I'm only going to write this just like this. It's x times 4 plus x plus 2. Don't distribute the x. We actually want that to cancel out right now. So let's see what happens in the numerator. In the numerator, the 4's cancel, right? 4 minus 4. So we're left with x over x times the square root of 4 plus x plus 2. And now something nice that happens is that these, so the 4's canceled, is that these x's cancel off. The x's cancel off, so we're left with the limit as x approaches 0 over 1 plus the square root of 4 plus x plus 2. And the reason why that was nice is because that x was giving us an issue, because that was the part that was making us divide by 0 after we try to plug in our 0. So basically we keep on simplifying until we can plug in our 0, and now we can. So now it's going to be 1 over the square root of 4 plus 0 plus 2, which is 1 over, ends up simplifying to 1 over 4. Okay, so let's do another one here. We have the limit of the square root of t squared plus 9 minus 3 over t squared as t goes to 0. So once again, we recognize there is a square root and 2 terms in the numerator. So we're going to multiply by the conjugate. The conjugate of the square root of t squared plus 9 minus 3 is the square root of t squared plus 9 plus 3. We have to multiply that in the numerator and denominator. So you can kind of see how if you don't know that little trick, it's kind of impossible to do this type of problem. So in the numerator, when you're multiplying those conjugates, what's going to happen is the square root, it's going to be the first one squared minus the second one squared. The first one squared ends up just canceling off the square root, minus the second one squared. 3 squared is 9. Okay, and then we're left with t squared times the square root of t squared plus 9 plus 3 in the denominator. Remember, don't distribute that t squared. And in the numerator, the 9's cancel, 9 minus 9. So we're left with t squared divided by t squared times square root t squared plus 9 plus 3. And hopefully you're kind of recognizing that this is the same, kind of the same concept as the other one that we just did, because the t squareds cancel off now. And we are going to be left with one more step. We have 1 over the square root of t squared plus 9 plus 3. Now we can go ahead and plug in our 0. And that's going to end up being 1 over the square root of 0 squared plus 9 plus 3. Simplify that, we get 1 over 6. Okay, so those are those two techniques. Okay, a couple other things for this section. let's find the limit of g of x as x approaches 1, where we have this piecewise function g of x equals x plus 1 when x is not equal to 1, and it's equal to pi when x equals 1. So the value of the limit as x approaches 1 does not depend on g of 1. So if we graphed it, it would actually look something like this, where it is the line x plus 1, except when x equals 1, then it jumps up to pi real quick. So the limit, as x gets closer and closer to 1, is actually going to depend on everything except 1 in this case, which is the function x plus 1. So the limit of g of x as x approaches 1 is going to equal the limit as x approaches 1 of that first function. And this is just direct substitution, right? So 1 plus 1, and that gives us a value of 2. So like I mentioned before, it definitely helps being able to draw this, or you can just kind of logic your way through this one. Okay, let's show, for this next example, let's show that the limit of the absolute value of x equals 0. So what we need to do is actually recall what the absolute value function is. The square root, or sorry, the absolute value of x is actually a piecewise function, and it's going to equal x when x is positive or 0, and it's going to equal negative x when x is negative. So hopefully that makes sense. It's going to equal whatever the x is when it's positive, so because the absolute value of 3 is just 3. But it's going to equal negative x when it's negative. That's because if you have the absolute value of, say, negative 3, then using this definition, that equals negative 3, which makes it positive. So the definition, even though it looks kind of confusing, all it's saying is it negates the negative values and makes them positive, which is exactly what absolute value does, right? So let's go ahead and take a look at this. Typically, when we want to show that a limit equals a number, we want to show that the limit from the right and the limit from the left equal the same thing. So I'm going to say that since the absolute value of x just equals x when x is greater than or equal to 0, that's going to be from the right. That means the limit as x approaches 0 from the right of the absolute value of x equals the limit of just x, because it's equal to x. This is going to be direct substitution, which is just 0. So we showed that the limit from the right is 0. Now we have to show that the limit from the left is 0. And sorry, I said I shift everything up there. So now we're going to do the opposite from the left. So since the square root of x equals negative x, so this is going to be the second line up here, for x being negative, that tells us the limit as x approaches 0 from the left of the absolute value is going to equal the limit of just negative x, which once again, direct substitution tells us that's just going to be 0. So since the limit from the left equals the limit from the right, that is our answer to the limit in general. So that is our answer for that. Okay, so now for the next example, let's prove that the limit of the absolute value of x over x as x approaches 0 does not exist. So just like before, we're going to do the limit from the left, the limit from the right, show that they're not equal, and that shows that this limit does not exist. So let's go ahead and start with the limit from the right of this function. What we're going to do is we're going to use the same idea that we did before and say that from the right, that means that it's to the right of 0. That means x is positive, so that means the absolute value of x just equals x itself. And now we're doing the limit of x over x, which cancels to 1. That's just a constant limit, so our answer is 1. So now let's go ahead and do the limit as we approach from the left. And just like last time, if we are approaching from the left of 0, that's negative numbers, we can replace the absolute value with negative x. And that ends up being negative 1, negative x over x, and that's a limit of a constant, so we get negative 1. So since the limit from the right does not equal the limit from the left, we know that the limit in general here does not exist. Okay, so not too difficult. You just have to know a couple little things there, and it's not too bad. Okay, so a few more things here. Here's another example. Let's say we have this piecewise function f of x. It's equal to 8 minus 2x if x is less than 4, and it's equal to the square root of x minus 4 if x is greater than 4. Let's determine if the limit as x approaches 4 exists. So hopefully we're getting a hang of this and we know what to do. To show that the limit exists, we need to show that the limit from the left equals the limit from the right. So let's go ahead and take a look at the limit from the right of 4 for f for f of x. So if we're going to the right of 4, that means we're using the second function, right? Because that's x greater than 4. So this is going to be the limit as x approaches 4 from the right of the square root of x minus 4. And all we have to do now is direct substitution. Square root of 4 minus 4, that gives us 0. Okay, and now we're going to do the limit as x approaches 4 from the left of f of x. Taking a look at the piecewise function, the limit from the left of 4 is going to be the first function. So that's going to be the limit as x approaches 4 from the left of 8 minus 2x. Once again, this is just going to be direct substitution. We plug in 4. That's going to be 8 minus 2 times 4, which is 0. So we know that the limit as x approaches 4 of this function does exist, and it equals 0 because the limit from the left equals the limit from the right. And they both equal 0. Okay, so that brings us to the last thing in this section, a pretty important theorem here, and that is the squeeze theorem. So this is also called the sandwich theorem in case you ever hear it. So let's say we have 3 functions, and our function is g of x, and g of x is squeezed or sandwiched between 2 other functions. So g of x is greater than f of x, but it's less than h of x. So g of x is completely sandwiched between these functions. Then if we know the limit for f, so let's say we know the limit for the smaller one, and we know the limit for h, and let's say that they're equal, and they're both equal to some number L. Since our function is sandwiched between them, then our limit for our function also has to equal that L value. So hopefully that makes sense. If we have one function between 2 other functions, then that means our y value has to approach the other one's y values if ours is directly squished between them. Okay, so graphically speaking, once again, graphically is always going to help a little bit. So we have 3 functions here. We have our middle function is g, and you can see how it's completely between these other functions, right? It's completely between these functions. So just ignore this little portion over here. We're not interested in that portion over there. So if we had the limit as x approaches a, you can see that h, you can see that the green one is going to L. You can also see that the blue one is going to L. Since ours is directly between it, that means ours also has to be going to L. Okay, so hopefully that just kind of makes sense. It's kind of obvious, right? So let's see how we're going to use this in a question. It gets a little bit more complicated the way that we have to use it. Let's show that the limit of x squared sine of 1 over x as x goes to 0 equals 0 using the squeeze theorem. So what we have to do is we have to set it up like this. So our function is this function, x squared sine of 1 over x. We need to find a function smaller than our function and larger than our function. And it doesn't have to be smaller than it and larger than it from negative infinity to infinity. It just has to be near 0 in this case because that is what x is approaching. Okay, so we want to make this as simple as possible. There's not always going to be one answer, one way to go about to find the answer, but we want to make it as simple as possible, and we need to pick functions that we ourselves can actually find the limit of. So depending on what the function is, we might do this different ways. So for now, I'm just going to put little question marks here. Something that is good to use, a little trick, if you have sine or cosine, we know that sine or cosine, the range is from -1 to 1. That is the range of sine and or cosine. So that is a great place to start because now we need to make this middle part look like, what we started with. And now all we need is an x squared, right? All we need is an x squared. So all we have to do now is multiply all three sides by x squared. So if we do that, that's going to be -1 times x squared, sine of 1 over x times x squared, and then 1 times x squared. And now what we have is our middle function is actually the function that we needed. Okay, so now we just have to make sure that the limit as x approaches 0 for both of these two equals 0, and that'll show that ours is also 0. Okay, so let's go ahead and check. Going to say the limit as x approaches 0 of the smaller one, that's just direct substitution, right? That is just plugging in because it's a polynomial, so it's -0 squared, which is 0. And then let's do the larger function, which is x squared. That's direct substitution again, so that is also 0. So we're going to say by the squeeze theorem, and since our function is squeezed between -x squared and x squared, we now know that the limit as x approaches 0 of x squared times sine of 1 over x also has to equal 0. Okay, so that is the squeeze theorem. Here's the graphs of x squared and -x squared, and you can see that the graph of x squared sine of 1 over x is here oscillating in between them, and you can just kind of see how it's sandwiched between them, and that one has to go to 0 also. Okay, so that's the idea here for this. But what you have to do is start with your function, and then maybe start with a piece of your function, in this case sine of 1 over x. Know that it falls between -1 and 1, and then you have to multiply the remaining part of the function onto it, and then show that the limit for both sides goes to, in this case, 0, so the middle one does as well. Okay, so that is it for this chapter.